Okay, our next speaker is going to cover something completely non-controversial, incredibly well understood, and airflow research in flex duct and sheet metal. And I need to tell you a little bit of information that you might not know about our distinguished speaker. Chris happens to be the director of M&M Manufacturing Company, but that's just a sideline. He ducts the risotto. He ducts all kinds of stuff. Okay? I mean, I don't understand why you would care about, duct work when you're truly a spectacular chef. We've known each other for maybe a dozen years, and I keep learning stuff. I had no idea I had a wonderful sense of humor and stuff. And so he is involved with a bunch of fairly significant research in terms of airflow resistance in various systems with a rather famous entity that he will talk about. So please give Chris a warm welcome from the summer camp.
You people are so easy. So if you were here in 2017, it's hard to believe that was 6 years ago, Allison Bales and I did a presentation on a very similar topic. We chose this as our first slide, and for the cheap sensationalism of it, to get a laugh, and it apparently still works. So we ended up calling the presentation "Joy of Flex." Get the rhyme there. And Allison and I spoke about problems with the typical installation of flex, the inefficiencies of it and so forth, the problems that it causes, and all of that. And I thought it was a pretty good presentation. However, my favorite part of the presentation was the way Allison started us out, which was juggling. So he juggled, and it was a great icebreaker and all of that, and it really helped everybody just kind of get into the program. So, Allison, if I get in trouble up here, I hope you still have balls. I'm a sheet metal duct guy. I love sheet metal, and if you've been in one of my classes or heard the presentation that I've done, you've heard me preach about the virtues of shiny, clean, durable, awesome metal duct. And you also heard me preach about the evils of nasty, flexible, wrinkly, bad, horrible flex duct. I talked about both. I've done a lot of that for about 40 years. And over the years, we've done a couple of research projects to prove that metal duct was better. I'm a member of an association called the Air Distribution Institute. We are an association of sheet metal duct manufacturers, and I'm the hired gun that's paid to go out and promote our products. The flex industry has Ralph Carber representing their side. Ralph and I are friends. We sit together on the ASHRAE 5.2 meetings, and but we are paid by competing industries to promote our products. So I'm a sheet metal guy. Our Air Distribution Institute, back about 20 years ago, decided to once and for all prove that sheet metal duct is better than flex. And we contracted with Texas A&M University, excuse me, their Energy Systems Lab. ASHRAE came in as a co-funding partner, and we actually handed over the management of the project to ASHRAE, TC 5.2. And in those days, we had Bass Abba Chakra came down representing ASHRAE. Bass had just finished a project a couple years before with Max Sherman and Ian Walker out at Lawrence Berkeley National Lab, and they were some of the first people to identify the problems with friction loss due to compression, which is the opposite of stretching, of this material. And they found friction losses up to about 9 times what was being reported. So they were some of the first people to identify that. Texas Electric Delivery came in, Lennox came in, and we blew air through ducts for about 2 years, spent $250,000. We followed strictly the testing protocols of ASHRAE Standard 120. We built a data acquisition cube, which has got a variable speed blower and a nozzle chamber for measuring CFM, and your entry duct is so many duct diameters. You got piezometer rings on either end, and the difference in pressure from one ring to the other is called pressure drop. We measured that for 2 years. We blew air through flex duct, metal duct, tried a few fittings, but mostly focused on the straight duct. We did CFD modeling, and you know what we proved? We proved that if you flow air through a curlicue, the air starts to curlicue. It does exactly that, and when it does, it's got more resistance and more pressure loss. Excuse me. So we did CFD modeling. We proved that the Darcy and Colebrook equations were absolutely correct, and everything that they predicted or stated with regard to friction loss, surface roughness, all of that were absolutely true. We built this ductulator, the ADI ductulator, and 8 years later, we completed the ASHRAE ductulator. It only took 8 years to build this because it was sponsored by TC 5.2 Duct Design, and try getting a room full of engineers to agree on anything. Even the colors and the fonts were hotly debated. So we did all those things, and I say big whoop. What we accomplished was to collect a bunch of data that says our product's better, and try selling any of those concepts like this to a homeowner. We needed data to help us sell our product, and what we came up with is data that is only interesting to some sick people like all of us in the room, and homeowners and even contractors are not really interested in all that. Well, I spent a lot of time thinking about how we could come up and make a case for encouraging people to at least consider sheet metal duct when they're building their homes. And I had met this gentleman a time or two at some various conferences, but we really got to know one another up here. And where's Andy? I know he's around here somewhere. Oh, he's right there. Okay. Well, too bad. So I love Andy. I told his wife last night I had a man crush on him. Andy Osk knows a lot of stuff about a lot of stuff, but I think the thing I like most about Andy is he's always thinking of the next question that we need to ask. He's always thinking of, how can we look at that from another direction? So I'm sitting at summer camp with Andy, I'm having a glass of wine, and I said, Andy, I want to do a research project, but this time I want to focus on energy use and something I can easily translate into like annual cost of operation. And but I said, I'm not sure how to do that effectively. And I said, my notion is maybe buy or rent a couple of houses side by side where we can lock them down, control who's coming and going, and let's equip one with metal duct and one with flex duct, and let's compare them for a year. But I said, that's going to be really expensive, and I'm still not sure whether the data that we pull out of that is going to be useful. And Andy says, Florida Solar Energy Center, which of course I'd never heard of. I did try and find a good picture of Andy on the internet to post here, but there's not one. So I assigned him this avatar. Florida Solar Energy Center. It's part of the University of Central Florida system. They're at their Cocoa campus, and they have these two laboratory houses. They're identical. They're side by side. They're real houses that you can do real stuff in. The floor plan is that of a 3-bedroom, 2-bath home. They're 1,300 square feet. They got 3-ton units. When we did our research, they had some Daikin units installed. And if you can see in the picture, They actually fabricated the walls but did not stand them up. They have them in there in racks where you can have airflow between them. And they did that so that the home would operate like a single zone. Really makes data collection a lot simpler and a lot easier. The homes were equipped with single-speed PSC motor carrier units when we first started working with the lab, but before we could actually get our contract kicked off, they had changed and put some two-speed Daikin units in, and so we had to decide whether to go with the single-speed or multi-speed, and because almost everything is going to multi-speed, we decided that for our data to be relevant for more years in the future, we wanted to go ahead and go with that. It complicated things a little bit, and we'll talk about that some more. We got our friends at Rite to do the duct design per Manual D. We did it exactly as it called for, including oversizing the flex duct, one duct size. So for instance, the trunk line coming off the plenum was 16-inch on metal, it was 18-inch on flex. And then everything was sized accordingly from there. We wanted the geometry of the duct system to be as close to one another as possible because we didn't want design geometry to be a factor in this. And as is the case with every job site, when we got in the annex, there was stuff in the way. And we couldn't go where we had planned to go, so we had to change some of the routing of the ducts, which actually added some length to some of the ducts. But we made a point of doing, if we had to do it in one house, we did it in the other house to keep the geometry the same. You can see what the duct installs look like. Excuse me. The metal duct was so pretty. I mean, look at it. The guys just, and we hired some really good contractors and paid them a lot of money to do it right. But I remember reporting to the ADI group, I said, this stuff is showroom quality. We're going to be proud of this for many, many years. And the flex duct, we made a point of installing it exactly as the flex industry prescribes, because had we done anything else, the flex industry would have just argued, well, you didn't install it right. So we installed it as well as it could be installed, and obviously did the same with the metal duct. When we were done, and we put the manometer on both systems, the total external static for the metal system was at 0.34 on high-speed fan. It was actually 0.24 on low-speed fan. The flex house was at 0.44 on high-speed and at 0.34 on low-speed fan, which is phenomenal for a flex duct system. It's really hard to get one that's designed and installed that well. I make kind of a big deal out of high-speed and low-speed fans. These homes were made to replicate what millions of homes in Florida had been built like back in the 70s, 80s, and even the 90s. And they're 8-inch concrete block walls, no insulation, half-inch furring strips on the inside with sheetrock on that, single-pane windows, and 6-inch fiberglass bats in the ceiling. And yet they perform very well down there. And again, this is Central Florida, just south and east of Orlando. The houses were perfectly content to operate on the low-speed fan the whole time. Only at peak afternoon temps for an hour or two would they sometimes kick into high speed, and when they did, they didn't stay in high-speed fan very long. So that was to the advantage of the flex duct. It helped it perform better at the lower velocities. We compared those studies, I didn't make that point, at what we consider to be best metal versus best flex. The difference in energy efficiency was about 5%. And that was disappointing for us metal duct guys because we were hoping to find much, much bigger numbers. So we ran it that way for a month or two, and all the time I'm thinking of what we're going to do next because we got $150,000 in this project, and I'm not liking the results. So what do you think I did? I screwed up the flex system. I found an article written by Rob Falk who was president of National Comfort Institute. Rob passed away a year ago. But he had written this for Contracting Business Magazine, and it was just the basics, the fundamentals of how to measure external static. And he went on to report that his company, his group, had done a national survey and had found that on average, total external static in residential systems is about 0.82. Now that's considerably higher than the 0.5 that equipment is rated at now. So 0.82 suddenly became a legitimate number for me to try, and so the task then became, okay, well, how do we manipulate that flex system to make it operate at 0.82? We're going to report that as an average system, and we're going to keep the metal as it was as our control. Now, it's at this point that it's really not fair to call this metal versus flex, because I've just screwed up the flex system. However, it is useful to know that we're comparing low static pressure to a high static pressure system. And so going through their study, coming up at 0.82, we felt like that was a legitimate number. And so I wanted to manipulate the flex system to run at 0.82. But before we did, I said, you know what, let's make that system run at 1 inch. And let's just record some data there. Because we know some houses are at an inch or maybe higher. It's actually not easy to make one perform that poorly if it's already a good system. We put a blanket over the return air, and it helped till it sucked it through the hole. We shut down all of the supply registers, and we finally got it up to 1 inch. And at 1 inch, our data started coming in quite a bit different, as you would expect. So the flex house, operating still at 0.34 on high speed, was running about 14% more efficient than the flex house at 1 inch. We're calling that bad flex. Still, kind of thought the numbers ought to be higher than that, but that's what they were. So how do you screw up a good flex duct system? Well, it's not that hard, actually. What we did was, add more length, add more turns and restrictions, create more sag and compression, and because of my experience building these ductulators, I had a pretty good idea of what we would need to do to reach that 0.82 static pressure. On the trunk lines, the trunk and branch system, as you saw, I cut them in the center and I added 30% more length. So if a trunk line was 10 feet long, we cut it, we added 3 feet, which induced all of the sag and wrinkling, compression and so forth. Branch lines, I cut them in the center and added 50%. So if it was 10 feet long, I literally added 5 more feet. It got really wrinkly like that. Added a total of 68 feet to a system that only had 157 feet. And so that's a 43% increase in material. And when we were done, and the guys were on the manometer when we were making the last connections and hanging the last ducts, came in exactly 0.82. Now, it was an educated guess, but I had reason to believe that that would be close to what was needed. So that 43% of extra duct that created all of the extra friction loss and the problems that we're about to see, that represents how much material is being wasted on new installations because they're using too much of it. And that's what creates all the problem. If you use a minimal amount, cut it to length, and install it, you're going to be fine. So test 3 is just that. We've got the flex house at 0.82, metal house still our baseline at 0.34, and I'm only 9% better. And again, disappointing. I just really thought those numbers ought to be higher. Here's how it breaks out. We did monitor the air handler units, the condensing units, and so forth. So if you'll look on the center column, the flex air handler unit, you can see that the delta between the flex house and the metal house was over 50%. Well, that sounds like a lot, but turns out ECM motors don't use much electricity. And a 50% increase of a small number is still a pretty small number. So put it all together, and we were about 9% better. And that's pretty much how we ran for the rest of the two years of this study. Well, again, big whoop. What did we prove? We were 9% better, and that's not going to blow anybody's dress up. It's not going to get a homeowner to make a financial decision to spend more money on his house just because he can save a few bucks on because of the duct system. So, as you might imagine, I was pretty confused. That's me, by the way. I was skinnier then. And then this happened. For over a year, no one set foot in the labs, and they were all connected. They could monitor the systems from their homes and so forth, but no one went in the lab. And towards the end of our contract, I was talking to Chuck Withers, our main investigator there, and he said, "Do you want to do anything else? You want to try anything else before we shut this down?" And I said, "I don't know. What if we lower the thermostat setting and let's just get some more cycles and see if it tells us something?" They'd been set on 75 for the rest of the time. So he goes in the metal house first, and just to change the thermostat. When he walks in, there's a big puddle of water on the floor. And he looks up, and there's a big wet spot on the ceiling. Big wet spot on the ceiling. And what he found was we had done some stupid stuff. What does Joe tell us not to do? Don't, say it with me, don't do stupid stuff. Well, we did some stupid stuff. And what we had done, I told you how pretty the metal duct was with all the wrap on it and everything. Well, the way you make duct wrap pretty is you overstretch it. You pull it too tight, but it makes it nice and smooth. It's all shiny and everything. You put the mastic on the seams or tape. And we had overcompressed the duct to the point that it was only 3/4 inch thick in some places. Well, R6 duct wrap is supposed to be 1 5/8 inches thick, and we had gone way past that. We had probably about R2. And in hot and humid Florida, guess what happened up in that attic? The less R value caused the surface temperature of the duct wrap to be cooler, and in some cases, in many cases, it was cool enough to start condensing and sweating. And so we understand now that it really is important to not overstretch your duct wrap. I mean, I've been in the business a long time, over 40 years, and I knew that they were overcompressing that wrap, but I mean, how much difference does it really make? Well, it turns out that's kind of a big deal. You don't want to do that. Stuff really matters. So when the moisture condensed on the outside of the vapor barrier, and because of the long run times, it didn't get a chance to dry out. And so what's the worst thing that can happen to your insulation system on your ducts? That right there. This is a catastrophic failure of the insulation system. They were literally standing in water because that condensation sweat beads all over the outside of the duct wrap. They wanted to go towards that cold spot, and they found ways of getting in there. We actually sent samples of the insulation off to the manufacturer, who told us that they felt like it was micro fissures in the FSK wrap, and it just had a capillary action, and the water made it in there. Whatever, had we not installed the duct wrap the way we did, and by the way, that's on me because I was supervising it, that would not have happened. So, fast forward, now we go back and look at our data that we collected, and what the researchers at Florida Solar Energy Center came up with is, if you had a full R6 insulation compared to the Flex House, the metal duct system would have been about 8% more efficient. And so that 9% that I told you earlier was probably closer to 17. And suddenly 17% more efficient, kind of a big thing. If we want to be serious, I get close on time. If we want to be serious about saving money, lowering emissions, lowering our carbon footprint and all that, I can get you something north of 10% just by putting in a better duct system. I'd love for it to be metal, but the point is we can actually do it with flex. We proved that you can do it with flex. It's just getting someone to do it. And with the new rating system for SEER 2, it's based on testing the equipment, rating it at a half-inch water column. Where is the incentive for an installer to install it to operate it a half-inch? There's not one. It's not in the codes. It's not anywhere. And where's the penalty if he doesn't install it that way? There's not one. So I'm introducing a two-step initiative, probably through ASHRAE 5.2, maybe through the Residential Building Committee as well. But I'm going to promote first a national survey. Let's get a larger sample, larger database of what houses really are testing at. And then when we get that, let's decide what this initiative should look like. Personally, I think the code should say you have to install the system to operate at whatever it was tested at. That's kind of a no-brainer. But there's problems with that. MERV 13 filters, HEPA filters, some of the high-efficiency evaporator coils have a lot of resistance. And so if you can't install to operate at a half-inch water column, let's at least acknowledge that and maybe recalculate the SEER and post it on that yellow tag that says, it came from the factory at 18, but it's running at 16 and a half. Anyway, that's an initiative that we're going to put out, and that's the end of my presentation. Any questions?
I have a question, Lena from NREL. So it's interesting, when you started talking about this, you had said, well, we want to do it exactly how it's supposed to be installed, and then you got to where, okay, well, the metal is still exactly how it should be installed, but the flex we're gonna mess with. Then it turned out that the metal wasn't installed as it should be. So I would think that if there's a chance to expand the study, what would be kind of maybe most relevant to like what's actually installed, in real homes that aren't research projects, is to kind of do that delta, like for each one for the metal, install it perfectly, test how it's performing that way, and then test how it performs on an average installation, not great installation quality, and then for each one, and do the same for the flex, and then you could find out how much the installation quality, affects the performance on each system, because I think that is probably going to be a lot more than your, 5 to 17% differences.
It could be. Honestly, knowing what we know now, I think we're probably going to go back and redo this whole series of tests and get some real hard numbers on it. But it's also interesting, the National Comfort Institute survey that came up with this 0.82 static for an average, that's flex and metal systems. It's all systems put together that they measured. So that was not a flex versus metal thing.
But you only applied it to the flex.
Right. Thank you.
I actually recommended the same thing, but I woke up with a piece of sheet metal in my bed.
Thank you. You got another one?
I would like to know two things. One is, if we're talking about savings and decarbonization, it looked to me like because you were using the FSEC houses, you picked the worst houses in the country. So your cooling systems were all in the attic, above the thermal boundary, and even if you save 17% in a house that uses $500 a year versus $3,000 a year, it's a totally different thing. So get people to insulate in the right place, and I think you'll have a much better system. And since you're talking about primarily what consumers choose, I think you're talking about new construction primarily. And they're not building, are they really building houses that bad in Florida? I could believe it, but.
Yes. Maybe. See, I want you to know it's not a Florida problem. It's a North American problem. Last question, and then we're going to get to talk about my favorite subject, which is water leakage.
Thank you. In addition to the testing that you did on static pressure within those systems, did you do any testing for duct leakage? And are you seeing any considerable difference between sheet metal and flex duct, considering sheet metal has a lot more seams that you need to air seal?
We did test all of the systems and actually found the leakage rate to be below what most people can even measure. They were both sealed very tight. And we compared air infiltration. One of the beautiful things about those two test homes is it can actually dial in to get air infiltration exactly the same in both houses. But both systems were extremely tight. And like I said, generally at a level that you couldn't even really measure and you put a number on it.
Warm thank you from the Westford crowd.